So hello, my name is Michael Opler, and I'm going to be talking about a complexity dichotomy for permutation pattern matching on grid classes, which is a joint work with Jelínek and Jakub Pekarek. So let me start by defining what a permutation is. So a permutation of length n is a sequence of n numbers from the set 1 up to n, and each of them appears exactly once. And it's often very useful to think about permutations as a set of points in the plane. And so permutation diagram of permutation pi is the set of points I, pi for every I, 1 up to n, in the usual Cartesian coordinates. So down here you can see permutation diagram of the permutation 3, 4, 1, 2. And when we say that permutation pi contains a permutation sigma, we mean that pi has a subsequence whose elements have the same relative order as the elements of sigma, and otherwise we say that pi avoids sigma. Note that this subsequence does not have to be consecutive. So down here we can see a permutation diagram of a permutation 4, 2, 1, 3, 6, 5, and marked red is an occurrence of a pattern 2, 1, 3. When we talk about containment, we often call permutations a patterns. And then a permutation class is just a down set of permutations, similar to graph classes, under this containment order we just defined. So whenever permutation pi belongs to C and some sigma is contained in pi, then also sigma belongs to C. And the easiest way to define a permutation class is by pattern avoidance. So for a pattern sigma, AV of sigma is the class of all sigma avoiding permutations. Similarly, for an antichain of patterns B, AV of B is the class of permutations that avoid every single pattern from B, and in that case we call B the basis of this class. And the simplest possible permutation classes is the class of 2-1 avoiders, which is in fact the class of all increasing permutations, and similarly the class of 1-2 avoiders, which is the class of all decreasing permutations. And throughout, we're going to often use these two symbols as a shorthand for these classes. All right. And so the problem we're interested in is permutation pattern matching, which given the input of permutation pi of size k and tau of size n, is to decide whether pi is contained in tau. And so in 1998, Bose and Lobif showed that permutation pattern matching is NP complete. And naturally, this motivated people to think about restricted variants of this problem, in particular, the C-pattern permutation pattern matching, or C-pattern PPM. And this problem is when we restrict the possible patterns just to a single permutation class C. So we have a permutation pi from the class C and an arbitrary permutation tau of size n. And the question is still the same, whether tau contains pi. And so in 2017, Jelínek and Kinchel completely resolved the hardness of this problem for classes defined by avoiding a single pattern. So the AV alpha pattern PPM problem is polynomial time solvable if and only if alpha belongs to this set of patterns, and NP complete for any other alpha. However, there's been different type of permutation classes that has been gaining attention lately in the literature, and those are the grid classes. So a K times L matrix whose entries are permutation classes is called a gridding matrix. And we can use this gridding matrix to define a grid class of M, which is denoted by grid M. And it's a class of permutations that admit a grid-like decompositions into blocks that belong to the classes of this matrix. In other words, it's a class of permutations such that we can cut them up into K rows and L columns in a way that each cell contains a permutation that belongs to the corresponding class in the gridding matrix. So down here, we see gridding matrix M on the left and a permutation diagram of a permutation from its grid class together with the cut lines. So we can see that this permutation belongs in fact to the AV132. This permutation is indeed increasing, this one is indeed decreasing, and this permutation avoids 3 to 1. And to each gridding matrix, we can also associate a certain graph called a cell graph. And that's a graph whose vertices are the cells of the matrix that contain an infinite class. And two vertices are adjacent if they share a row or a column, and all cells between them are empty. So here in the matrix, you can see the edges of the cell graph, which is in fact just the path on 4 vertices. Now let me take a short detour and define a width measure on permutations called grid width. So for a set of integers A, the intervallicity of A is the size of the smallest interval family whose union is equal to A. So essentially it says how many consecutive integer intervals we need to obtain A via union. And for a subset S of the permutation diagram, the grid complexity of S is the maximum of the intervallicities of its index set and value set. So down here we see a permutation diagram and its red subset. And this subset has grid complexity 2 because both its indices and its values span 2 consecutive integer intervals. And we can use this grid complexity to define grid width measure in the usual way. So we take a rooted binary tree with n leaves when each leaf is labeled by a distinct point of the permutation diagram. We call this a grid tree. And then by this p subscript v superscript t, we denote the point set of labels in a subtree that is rooted under v. And the grid width of a vertex v is then just the grid complexity of this subset of permutation diagram. And the grid width of the whole tree is, as usual, just the maximum grid width of a vertex in this tree. And the grid width of a permutation is then the minimum attained over all possible grid trees V. And we denote the grid width by GW of pi. And grid width is tightly connected to permutation pattern matching, as suggested by the following theorem. So whenever we have a permutation pi of length k and tau of length n, so we can decide whether tau contains pi in time n to the big O of grid width of pi. This follows from, well, Hal and Rabinovich first showed that this holds for a different parameter called tree complexity, and later Jelínek, Opler, and Walter showed that grid width is in fact up to a constant equivalent to this tree complexity. So then this theorem followed. Let me remark that in fact one can obtain the approximation of the optimal grid dip composition in the same time. So in fact, you don't have to have the grid tree specifically in hand in order to solve the ppm matching. All right, so now let us focus our let us look at the monotone grid classes, which is just a small set of grid classes, and we say grid class grid M is monotone if M contains only the increasing classes, the decreasing classes, and empty entries. And so in 2017, Nu wondered at the end of his PhD thesis, he asked, well, what is the complexity of grid M pattern ppm for such class, for a monotone grid class? And we actually answered this fully. So the following dichotomy. For a monotone gridding matrix M, one of the following happens. So either its cell graph is a forest, the grid matrix has bounded grid width, and the corresponding decision problem can be decided in polynomial time, or cell graph contains a cycle, then the grid class has unbounded grid width, and the corresponding ppm problem is NP complete. So we're going to focus on only one part of this, and that's when cell graph contains a cycle. And what is the important implication of this fact? So this is stated in the following lemma. So when we have a monotone gridding matrix M such that its cell graph contains a cycle, then for every integer p at least 1, there is a gridding matrix N such that the grid class of M contains grid class of N as a subclass, and the cell graph of the matrix N is a path of length at least p. So we can generate subclasses of grid M that are still grid monotone classes, and their cell graph is arbitrarily long paths. So a brief proof sketch. So let's look at the picture down here. So we start with a monotone grid class whose cell graph is a cycle, and we replace each cell with an appropriate 3x3 matrix. In generality, it would be k times k. So every increasing class we replace with diagonal matrix of increasing classes, and every decreasing class we replace with anti-diagonal matrix with decreasing classes. And via this, we obtained a subclass of the original class, as witnessed by these thick dotted lines. And when we look at the cell graph of this new class, then you can see that it consists of 3 individual copies of the original cycle. Or in general, we would have k individual copies of the original cycle. However, now if we look at this red cell and replace the diagonal with an almost diagonal, with the subdiagonal, and shift the cells, shifted by 1 up, then we actually connected those copies of cycle into one long path. So if you start in this blue cell, then you can actually make sure that the whole cell graph is a single long path. And still, as witnessed by the thick dotted lines, this permutation class is still a subclass of the original grid class. And so what are the implications of a cycle then? Well, first is the lemma that whenever you have a monotone gridding matrix such that its cell graph contains a path of length k, then there is a permutation in grid class of M that has grid width at least k over 4. So in some sense, the longest path in the cell graph gives a lower bound for grid width. And so in particular, if the grid class has a cycle in its cell graph, then we can generate subclasses with arbitrarily long paths, and therefore the class itself must have unbounded grid width. And so, for the second part, if the cell graph contains a cycle, then the grid and pattern PPM is NP complete. And so in 2017, Jelínek and Kinchel showed that AV3-to-1 pattern PPM is NP complete. And so the class of AV3-to-1, the 3-to-1 avoiders, can be also described as the class that's obtained by interleaving 2 increasing sequences. And moreover, it can be described as a class of permutations that can be drawn from this infinite staircase, from this like infinite path of increasing classes. And so what we, up to a lot of technicalities, we essentially take their reduction, their pattern from AV3-to-1, and then map it to the long path in the grid M. So we generate a subclass of the grid class that has a sufficiently long path in its cell graph, and then just map the pattern from the staircase path to this general path of grid M. Okay, so now we continue to the situation of general grid classes. So first, let us define a horizontal monotone juxtaposition, and that's just a monotone grid class which contains 2 non-empty classes next to each other. And similarly, a vertical monotone juxtaposition is just a monotone grid class that contains 2 monotone classes on top of each other. And we say that an ordered pair PQ of vertices in the cell graph is a bumper if either the entry corresponding to the vertex Q contains a horizontal monotone juxtaposition and those 2 share the same column, or if it contains a vertical monotone juxtaposition and the 2 entries share the same row. So down here, we can see 2 examples on the bumpers on the left and in the center. So the entry corresponding to MQ contains a horizontal monotone juxtaposition and they share the same column. In the center, it contains the vertical monotone juxtaposition and they share the same row. And here on the right, you can see an example of something that is not a bumper because the entry corresponding to the vertex PQ contains a vertical monotone juxtaposition, but the 2 vertices share the same column. And then a bumper-ended path is just a path in the cell graph such that it both starts and ends with bumper. So both the vertices P2, P1 are bumper, and Pk-1, Pk are bumpers. And so why is it important? Well, it turns out that whenever the cell graph contains a bumper-ended path, then the grid class has unbounded grid width, and the problem grid M pattern PPM is NP complete. And so let me sketch why this is true via a picture. So here we see a cell graph, a grid class with cell graph which is a bumper-ended path. So since it's a bumper-ended path, we can replace these end vertices with the monotone juxtapositions. And since everything in between are infinite classes, we can replace them with their corresponding, with either increasing or decreasing class. And so we obtain this, which is a subclass of the original class. And now we can refine each of those middle cells into 2x2 matrices using the same trick we already saw before. And what we obtained is a subclass of the original class, but moreover, it's a monotone grid class that contains a cycle in its cell graph. And therefore, the unbounded grid width and the hardness of the grid and pattern PPM follows from the results about monotone grid classes. We can complement this with this proposition, which says that if every entry of M has bounded grid width, so we restrict ourselves to gridding matrices such that each entry of M has bounded grid width. And in that case, if the subgraph is a forest that avoids a bumper-ended path, then in fact the class grid M has bounded grid width. And as we already said, in such a case, a grid M pattern PPM can be solved in polynomial time. We omit a proof of this here since it's quite complicated. But let me just say that we explicitly generate the grid decomposition of bounded grid width. So to summarize, what we have shown is that when we have gridding matrix M whose every entry has bounded grid width, then one of the following happens. So either the cell graph is a forest, the grid width of the grid class is bounded, and the corresponding PPM problem is polynomial time solvable, or the cell graph contains a cycle or a bumper-ended path, in which case the grid width of grid M is unbounded, and the corresponding PPM problem is NP complete. So let me end by stating a few open questions. So first of all, the grid MP pattern PPM problem, or in general the C pattern PPM problem, is defined by restricting the pattern to belong in class C. However, different problem is when we restrict both the pattern and the text to belong to the class. So we ask, is there any monotone gridding matrix M such that the grid M pattern PPM is NP complete? But we can decide in polynomial time whether tau contains pi if both pi and tau belong to grid M. And the second, perhaps more important question, in all cases we know it's true that C pattern PPM is NP complete if C has unbounded grid width. So we ask whether this is a general thing, whether it's true that C pattern PPM is NP complete if C has unbounded grid width and polynomial otherwise. That's it. Thank you for your attention.